Assalamualaikum and very good day. So today I will be presenting about the thermal power plant for monitoring and control. So we are from group number 1. This is our group members. For introduction, thermal power plant convert heat into electrical by using high pressure steam to derive turbine. To ensure safety, we must preciously monitor and control 4 critical parameters, which is pressure, temperature, flow, and level. By utilizing a synthetic egg cycle, our project used industrial-grade sensor and lab view logic to maintain the delicate balance, preventing equipment damage and ensuring peak operation efficiency.
Assalamualaikum and good day. In this video, I will explain the application of instrumentation in a thermal power plant focusing on a pressure monitoring system using a GS4200 pressure transmitter. In application, thermal power plants generate electricity by converting heat energy into electrical energy using high pressure steam to drive turbines. This instrumentation system is applied in a thermal power plant to monitor steam pressure. The GS4200 pressure transmitter measures the pressure inside the steam pipeline and sends a 4 to 20 mA signal to the control system. This allows continuous monitoring to ensure safe operation and prevent overpressure conditions. Excessive steam pressure can cause hazards such as pipe rupture or boiler explosion, while low pressure prevents the turbine from rotating. When the pressure reaches 7 bar, a LED indicator is activated as a safety warning. Next, I will explain about identification of instrument. I use GS4200 pressure transmitter. It is an industrial pressure sensor designed to measure steam pressure in thermal power plant system. Therefore, a 4 to 20 mA current signal is preferred over 0 to 10 voltage signal, as the current signal are more robust and less susceptible to electrical interference. The transmitter provides a standard 4 until 20 mA output signal proportional to the measured pressure and commonly used for monitoring and control application. Now, I will explain about simulation, which is block diagram. According to the features above, from figure 1.2, the raw signal is processed using signal conditioning to convert electricity into physical unit, which is bar. The system simulates an industrial pressure monitor using an ES1 GS4200 transducer. Since the sensor outputs a 4 until 20 mA current, a 250 ohm resistor is used to convert the signal into 1 to 5 volt for the lab view. The process data is visualized in a real time via a vertical pointer slide and a waveform chart. To ensure system safety, a Boolean comparison monitors the pressure against a 7 bar set point. The gain of 0.625 is derived from the 10 bar range divided by 60 mA spark. If the value exceeds this limit, a red LED alarm is triggered immediately to alert the operator. Next, I will explain about the datasheet. Based on the operating range and accuracy specified in datasheet, the GS4200 is appropriate for steam pressure monitoring application. It supports low to mid pressure range 0 to 10, making it suitable for simulating power plant pressure control system. Although actual industrial boiler typically operate a higher pressure, the GS4200 is adequate for pressure monitoring and control simulation in lab view, fulfilling the objective of the project. In conclusion, the purpose of lab view circuit successfully simulate an industrial pressure monitoring system using a GS4200 pressure transducer. The design demonstrates proper signal conditioning.
Assalamualaikum. So next I will be presenting on temperature monitoring and controlling for instrument Oleum Tech HRTD with PT100 RTD sensor. So manufacturer is from Oleum Tech Corp. Application of the instrument in power plant environment. This instrument is critical for boiler monitoring, specifically tracking feed water and high pressure steam to maintain thermal efficiency. It is built for extreme, operating safely in pressure up to 6,739 psi and in hazardous zone thanks to its explosion-proof design. To ensure data accuracy near large generator, it used a 4 until 20 mA signal which is highly resistant to electromagnetic noise. So technically, this device is identified by its 316 stainless steel construction and IP66 rating, making it both corrosion resistant and dust type. It covers a wide measurement range from negative 50 degrees Celsius until 400 degrees Celsius with an impressive accuracy of plus minus 0.2%. A key feature for Revati is stability, which is rated at 0.1 degrees Celsius per year, ensuring long-term precision with minimal maintenance. To test this system safely, we developed a digital twin in LabVIEW using a while-loop architecture. We implement a scaling logic where each row milliampere signal is converted to Celsius using the formula Y is equal to 28.125x minus 50. So our result developed the logic. 4 milliampere correctly read as a negative 50 degrees Celsius, while 20 milliampere triggered the red LED for a critical overheat at 400 degrees Celsius. The simulation proved how digital innovation support SDG 7 and 9 by optimizing fuel efficiency and preventive infrastructure failure through optimized safety. So this is the datasheet for technical specification for this sensor.
Hello, my name is Muhammad Syafali Kalbin Burhan, number metric CE250016. Today I would like to present our solution for level monitoring and control. So, in a thermal power plant, a single level error can lead to equipment failure. Our level monitor and control system is designed to eliminate that risk. We utilize the UE3003 ultrasonic. It's a non-contact high precision tool with a range up to 50 meters. It feeds real-time data directly to a centralized dashboard via standard industrial signal like RS485. The system is fully automated. If level hit critical high or low, it triggers a visual and 800 Hz audible alarm. This prevents boiler from dry boiling and keep water out of your turbine. The bottom line, by choosing the UE3003, you just measure water. You ensuring operational stability and protect your plant most expensive asset. Simple, precise, and reliable. And then second is our system focus on high precision water level management for thermal power plant. We use the UE3003 ultrasonic sensor, which provide non-contact measuring with up to 0.25% accuracy. The data is processed through a LabVIEW block diagram. It converts water level into power output using the formula power equal level over 10 times to 100. System operation during normal operation, levels stay between 2 and 8, maintaining a stable 40.8 megawatt output. At the high level, at a level of more than 8, it's been the max light and 800 Hz alarm triggered to prevent water from entering the turbine. At a level less than 2, it's minimum light activate and power is reduced to stop the boiler from overheating. So, and the last one is I will show you a technical specification, and this is the technical specification for UE3003 ultrasonic sensor. And the last one is dimension UE3003 ultrasonic sensor. That's all from me. Thank you.
This section focuses on monitoring and controlling flow in a thermal power plant. The instrument selected is the Proline ProWheel F200 Vortex Flow Meter, which is widely used to measure steam flow. Accurate flow measurement is essential because steam is the main working fluid used to drive the turbine and generate electricity. Flow measurement is one of the most important parameters in a thermal power plant. Steam flow directly affects boiler efficiency, turbine speed, and overall power output. If the flow is unstable, the plant efficiency will drop and safety risks may occur. Therefore, continuous monitoring and control of steam flow are required. Flow instrumentation is used to measure, monitor, and control steam flow inside the plant. In a thermal power plant, flow meters are installed at the boiler outlet or turbine inlet. The measured flow data is sent to the control system such as PLC or DCS for real-time monitoring and automatic control. When steam flow is too low, the turbine will not rotate efficiently and power output decreases. When steam flow is too high, it causes mechanical stress and damage to the turbine. Therefore, controlling steam flow helps maintain safe operation and stable electricity generation. So, the instrument used in this project is the Hauser Proline ProWheel F200. It is a vortex flow meter designed specifically for steam, gas, and liquid measurement. This type of flow meter is commonly used in power plants because it is reliable and suitable for high temperature steam. The ProWheel F200 operates based on the vortex shedding principle. When steam flow passes a valve body inside the pipe, vortices are formed alternately. The frequency of these vortices is directly proportional to the steam velocity. The sensor detects this frequency and converts it into a flow rate signal. One major advantage of this flow meter is that it has no moving parts. This makes it more durable and reduces maintenance requirements. It can withstand high temperature and pressure, making it suitable for steam application. It does also provide stable and accurate measurement over long-term operation. In this project, a LabVIEW-based system is developed to simulate flow monitoring and control. The system allows user to input flow values and observe the response in real time. It does also include safety indicators to show whether the flow is within acceptable limits. On the front panel, a knob is used to simulate the flow input. The calculated flow rate is displayed numerically and visually using a gauge. Two LED indicators are used to show minimum and maximum flow conditions. This interface allows operators to easily monitor the flow status. In the block diagram, the knob input is curled to produce a flow rate value. The flow rate is compared with predefined minimum and maximum limits. If the flow is too low, the min flow LED turns on. If the flow is too high, the max flow LED activates. This logic simulates industrial flow monitoring and alarm system. During normal operation, both LED indicators remain off. When the flow rate drops below the minimum limit, the min flow indicators light up. When the flow rate exceeds the maximum limits, the max flow indicator turns on. This provides immediate visual feedback to the operator. The LabVIEW simulation represents the real operation of the ProLine ProWheel F200. The knob represents steam flow in the pipeline. The gauge and numeric indicator represent the flow display on the actual instrument. The LED indicators simulate alarms used in industrial control system. This simulation demonstrates how flow monitoring and control work in a power plant. While LabVIEW is used for learning and simulation, the ProWheel F200 performs this function in real industrial environments. This simulation helps us understand how accurate flow measurement improves safety and efficiency. So this is the datasheet for vortex flow meter. So in conclusion, flow monitoring is essential for safe and efficient power plant operation. The ProLine ProWheel F200 is a reliable instrument for steam flow measurement. The LabVIEW simulation successfully demonstrates flow monitoring, visualization, and alarm logic. This shows the importance of instrumentation in modern thermal power plants.
In conclusion, this project demonstrates that a robust monitoring and control system is the backbone of the power plant safety. By simulating industrial instruments, we have successfully integrated the temperature, pressure, flow, and level monitoring by scaling DR4 until 20 mA signal in LabVIEW. We validated a syn-think-act cycle that effectively prevents critical failure like boiler dry boiling. Ultimately, this digital twin proved that precisely instrumentation not only protects infrastructure but also ensures the sustainability energy production in line with SDG 7 and 9. That's all from us. Thank you.